Okay. All right. So let's get started. So we're so I'm going to recap what we did last time and continue. So our story is trying to understand the theory of automorphic forms via this formalism of arithmetic quantum field theory. And let me recall some things. I'm also going to use some things that Brian explained. So just as as context for some of the things I said before, if you have a four-dimensional topological quantum field theory, then you get this is the picture I drew. You think of a point in space-time. You ask yourself, what can you insert at a point? What kind of measurements you could do at a point? And that's captured in this Bordism kind of formalism. As you cut out a little ball around this point, and the states on this little sphere are all the labels of what you could put at this point. And so this is the value of the theory on a free sphere. This is what give the local operators. That's the space of local operators, and they have a structure. The structure that is that if you take two of them at nearby points, you can think of including them inside of a bigger ball, looking from a distance, and that's a kind of version multiplication. And they form what Brian explained, which is an E4 algebra. And that's just the algebraic structure given by pictures like that. So that's the kind of structure, and they act. If I have a three manifold, here if n is a three manifold, then this algebra acts on the vector space attached to a three. That's kind of part of the structure. We also can do something one level down. If I think about a line instead of a point. So you can look at the link of the line. I think I misused the word last time, but the link of a line in 4 dimensions is a two-sphere. And so you could think of that. So the idea is that we said that a field theory attaches a category to something in 4 dimension 2. A 4-dimensional theory attaches a category. And this is going to be the category of line operators or line defects. So this category, in the same way, kind of we think of it as describing what kind of singularity or what kind of phenomenon is happening around this point as you approach it. So there's a category of line operators. And one of the, for me, I think the most compelling reason why category theory or higher category theory comes up in quantum field theory is, I ask, why is this a category? Well, I kind of made it axiomatically a category, but why should line defects have anything to do with the category? And the basic picture is that you can imagine one kind of line operator going around at one point, and then another line operator at another point, and there could be an interface between them. So in physics, a very natural thing to do is talk about interfaces between line operators. You can have a line operator here and another line operator here, and there's something some kind of space of morphism, which is the interface between them. So the fact that line operators form a category is because you have interfaces between them. And all the categorical structures we'll see can be basically boiled down to this kind of thing. So that's fundamentally where categories are coming from. So they form a category, but you can...
And the interfaces have a product which is associated.
That's right. And the interfaces have a product, which is I can have another. I can collide. There's an operator product expansion of these interfaces, which is a one-dimensional, which is kind of an E1 structure, which is an associative multiplication. So they form a category. That's one statement. But we could also do this kind of collision structure. That kind of collision structure could do an operator product expansion of line operators. If I have another line operator, I can think of them as colliding. And that, if you like, is again the same picture. I only know to draw one picture of spheres colliding. And so now we get an E3 category. We've lost one dimension. We get an E3 that's slightly less commutative, but still pretty commutative category of line operators. So that's the structure we have. These are the two things along the line and transverse the line have now broken apart. Before it was all in that 4, here it's kind of 3 plus 1 is that same. Okay, so so this is and again this category will act on various things. This will act on the category attached to a 2 manifold. So if you have a 2 manifold, I could draw pictures like this, where these lines are kind of sticking perpendicular to the board. And so the category attached to a 2 manifold is acted on by this category. Okay, so that's and moreover, okay, and let me say one more thing before we relate this to automorphic forms. In what I had last time is I didn't really have this lines. I took a loop. I took a clothesline. So another thing I could draw is I can take a loop in 4 dimensions, and it's now the boundary of its tubular neighborhood is now, S2 cross S1. One of the few facts that I want to use again and again about topological quantum field theories is crossing with a circle is taking a trace. Here it's taking a trace of an identity, or it's a dimension, but it's a version of a trace. So the value on S2 cross S1 is the trace of the identity operator on Z of S2. So you get kind of labels for loops from your labels for lines. You have this category of line operators, and then you could take its trace, also known as Hochschild homology, and that's where loop operators come from. Yeah.
So Z of N is a module category for this E3 category.
That's right.
Is it an E2 module category?
No, it's just a left or right depending on my side. It's not a. It's just I can only attack from one direction.
No, but is it E2?
It's a module for this E2.
The E3 category. Yeah, I don't see.
No, it's an E3 category. It's just a left module for an E3 algebra. I have a notion of a left module. I have a notion of a E3 module, and it's not no. This guy is just a left module. Can only attack from one side. That's all this structure.
It's just a category. It doesn't have any.
No. Yeah, it's just I guess the way I wrote it, make a right module.
But it's a module category.
Yeah, it's a category, which is a module, but it doesn't have any additional structure. Just a module for this. I mean, if you like, there is additional structure in that I could do it. It's kind of factorizably. Maybe we'll say more about that. But I can attack at different points. Really, I have, if you like, so it's really a module for the factorization homology of this category. But that's.
Let me try to understand the picture. So you're having the lines that are acting on Z of N are coming in from the bulk. Right?
Yeah.
You could also have lines that stretch across.
Yeah, there's lots of pictures. I mean, but
you're not doing that. I just want to make sure that's.
I'm not doing that. Yeah, no, that's something else that maybe I'll do it. I did that last time. This is not what this. That's what I'm not. Okay, so now how does this relate in our theory of automorphic forms? We had so I talked a little about the local operators. The local operators in the theory of automorphic forms are not super exciting. They are an E4 algebra. In fact, they're just a commutative algebra. It's just the homology of a classifying space. It's not super cool, but they're useful. But where things get more interesting is so in this. So I have this wannabe theory of automorphic forms, which is something like an arithmetic version of a 4D QFT. And in this theory, the line operators. This is the category of representations of the Langlands dual group, which hasn't appeared so much last time. Just to say there's a community. It's some derived, a smarter derived version of this. So let me not. That's why I'm not writing equals. But it's pretty much so. This is what's in the Hecke category, the spherical Hecke category. That's the name for this. Where sphere has nothing to do with this being a sphere. From, I guess it's the same as two, from representation theory. But now, this is the spherical Hecke. That's the thing that labels the Hecke, the operator. And this guy is a tensor category representation. Dual group has a commutative tensor product, which is some shadow of this E3 structure. But the thing that appears more classically in the theory of automorphic forms is the trace of the identity on this. I mean, it's really the value on S2 cross S1, which I'm just gonna decategorify this. Also, in this case, you could also say K group, and which is just the representational ring. Maybe again, I'm ignoring some dryness. It's the representational ring of this. So that's then my suggested notation for the ring, the commuting ring of representations. And so those are the loop operators. And the pictures we drew last time is to say that if I give you the space of automorphic form, so I look at AG on an arithmetic 3-manifold, and my example, so this could be, for example, something like spec of the ring of integers on a number field or a global field. This will be a module for this representation ring that you check, and that's somehow exactly this picture. Here's my 3-manifold plus time, and then I'm looking at loops in here. Yeah.
Maybe I'm misunderstanding, but in that thing you're on the left,
Yeah.
it's supposed to be a trace of convenience, really,
Yeah, okay. Yes, yeah. So I'm going to be, so I mean, this is a true statement. It's maybe not the most relevant true statement. Yeah, so thank you. So I mean, that is relevant in some places if I'm crossing with a circle. So really here, because I'm wrapping around, like not in sort of a naive circle, I'm wrapping around a prime. What I really want is the trace of Frobenius on this, which also looks very close to this.
I mean, you need, okay, I don't understand. You need a trace of Frobenius for what to be true?
The thing that's actually acting is the trace of Frobenius on this category, and it ends up being basically the same. So if the group is similar.
Now I'm totally confused.
Yeah. Yeah.
Just because of like the formalism. At least
Yeah.
Before I understood you had a category and you had something called the trace of a category.
Yeah.
You had already introduced that.
Yeah.
But now
Yeah.
the trace of Frobenius will be like, is what? Is an operator?
Yeah. So if I got by with this. You should have probably complained earlier, right? But I mean.
No, I didn't. I was fine until the question.
Okay, no, I mean, so the point is, so let me just write down, if I'm in, let's write everything, it's very, specifically let's be in a context where I know what everything means. And so let me even take my arithmetic 3-manifold, right? To be, I have a curve over a smooth projective curve over a finite field. Right, and then, and I think of this as the mappings torus of this Frobenius endomorphism acting on the curve over the algebraic closure. Right, so that's the picture we drew last time. We have this Frobenius. So now what is the relevant Hecke category? So let me call this guy. So what is this? Let me call this a Hecke category, and this is the Hecke algebra. My notations. So the Hecke category, the category that I'm saying is the category of line operators, has this description. I can deduce this from other things I've said later, but let me just write down something. So you look at the group G over my local field. So here FV is going to be FQ. T. So this is going to be my group, and I look at maybe I should just not try to introduce so much notation. So I have FQ Laurent series T, and I look at double coset for FQ Taylor series T. So this is the affine Grassmannian. This is the FQ bar version of the affine. Ignore FQ bar, basically, it's an algebraically closed field. So just picture the complex numbers. So look at affine Grassmannian, and then you look at equivariant sheaves. So this is, I'll write it in FQ. So this is in less annoying notation. Maybe this is the loop group, the positive group loops. That's the affine Grassmannian, and positive loops again. Where are these annoying loops coming from? This is because I'm thinking about this sphere as two disks looped together. But it's kind of the same as sequentially, so that's why they're both LG pluses. But okay, so that's where this picture is. I said this was about S2, so that's what this category is. And now this,
So you do the double.
Double
You're
cosine.
not looking at equivariant sheaves, you're just looking at sheaves on this. double cosine.
that's a different terminology for the same thing. So sheaves on the double cosine just means equivariant sheaves, like the Riemannian, and look at equivariant sheaves on it. And that's what this picture is. Those are the line operators. That's the spherical Hecke category, that by definition. And now this carries a Frobenius. This everything here is defined. G is defined over FQ. So everything here has an action of the Galois group of FQ bar over FQ. This whole thing is, and so this space carries an action. It's right, and everything here is defined over FQ. This whole category is defined over FQ. It has a Frobenius endo functor, and I can take its trace. I'm not going to define the trace of given a category and a functor. There's a notion of trace, which is a vector space.
But did you write FQ bar there or FQ?
And these are bars.
Okay, good.
Yeah.
Uh-huh.
Yeah, this is the geometric guy, right? This is the category. It's a geometric guy, and then when I cross with the circle, and Sanath is pointing out, my circle is a interesting circle. It was a Frobenius circle. So what I really want to do is take trace of Frobenius here, and trace of Frobenius by the function sheaf correspondence. What the Frobenius trace here is doing is exactly the function sheaf correspondence. So I get the Hecke algebra, which is functions. And again, I haven't been careful about where my coefficients are, so I'm just going to keep writing functions on FQ Laurent series T. Now I do mean FQ. Okay, this is getting annoying to write, so let me write cheap.
I see. So the comment,
And this is the trace of Frobenius. So taking the trace of the Frobenius, I get this algebra, which is the spherical Hecke algebra.
so the comment was that where you were trace the identity, it should be traced from.
That's yeah, and that my circle. I really am doing some interesting circles, and that's the thing that's relevant. Yeah, thank you. Okay.
You out it's wrong.
I was out of that chop, but I'll find some. There's very simple. Please. Okay. Okay. So this is the algebra that act. This is the spherical Hecke algebra. These are the Hecke operators that act on spaces of automorphic. I'm writing the function field version to do various variants, but this is the thing that acts on spaces of automorphic forms, and this is how it appears from a TQFT picture. Okay. Great. So now, so this was my version of a review of last time. Now, what I'd like to go is go one level up. I want to now, so what is my goal here? My goal is to add more and more structure and try to tell you what it is classically, right? So I'm going to go to more and more defects. So I had a point operator, I had a line operator. Now let's go to a surface operator. So here now I have a two-dimensional defect. So again, I'm in 4 dimensions. I'm in 2 dimensions. So I don't really know how to draw this. The link of this is a circle. Link of a 2-manifold in R4 is a circle. So the surface operators or surface defects, they form, and let me write the words on the outside, an E2 category. So again, the important thing to notice just is 2 plus 2 is still 4. There's still 4 directions that are going on, except now, why are there 2 categories? It's the same picture. If I have one surface defect and another surface defect, you can talk about interfaces between them, but now you can talk about interfaces of interfaces. So that's why higher categories are appearing. Okay? So they form a 2 category, and why E2, I can still collide them. I still have this OPE, I just don't have as much room to do it in. That looks like little circles inside of a big circle. That's the transverse picture. So it's a little less commutative still. Thank you, Dan. Okay.
So, the transfer spaces was not too. So.
Yeah, it's not super commutative. So on some level you start noticing. So an E2 category
Rating or something.
Yeah.
Okay.
And that's all of these ENs are referring to every EN. E1 is what you like to say infinity or associative. Every higher one in some level looks commutative. On level of cohomology of vector space is commutative. But say E2 category is a braided tensor category that's honestly non-commutative. So so there's some honest non-commutativity here. But okay, so that's what you're supposed to get. Now, what I need to, this sounds very far from an automorphic form, so let's, we're gonna kind of go down in dimensions to relate this to something. So I want to claim again that this structure is labeling something very, very classical in automorphic forms, namely it has to do with ramification. So it has to do with level structure. So first of all, maybe I should just write something. I wrote this last time. What is the thing I want to attach to a circle? Okay, I need to tell you what I mean by circle. You can have various versions of a circle, something like a punctured disk. Let me be, here's an example. This is an example of a circle. Take algebraically closed field, Laurent series T. That plays the role of a circle. It's kind of just monodromy, that's fundamental group. And this I claim was some annoying two category, annoying just because we know relatively little about it. It's super interesting. And this is G of this field categories. There's some collection of categories which with an action of G of this field.
Categories with that action.
Yeah, representations of this group, but not on vector spaces, but on categories. So that's that's the claim that that's what these guys are. That's what surface defects are labeled by. But okay, so that's a little. So what's an example? An example would be, well, how do you write representations of a group? The easiest example is find a space in which the group act and linearize it, right? So if I want to find, so if I have this group, let me call this field F's are confusing and FVs are also annoying. So let me call this K. Okay, that's the field. So what's an example of a G of K category? Well, you just take a coset space, for example. Take G of K mod your favorite subgroup. So for example, G of the ring of integers, or maybe inside of here, there's the Iwahori subgroup, or take your favorite congruent subgroup. So, take your favorite subgroup, but look, I like congruent ones. And you look at the category of sheaves on this space. That's a category. The space is acted on by the group. So that's what I mean by a categorical representation. This is the kind of thing. And again, it's the kind of thing that if I take a Frobenius trace, I'll get a space of functions on the code. Get something kind of classical. So yeah, this maybe I should just write that, right? This guy has again an action of Frobenius, and if I take this trace of Frobenius on this category, what I get is the space of functions, smooth functions, on G here. Now it's FQ along series T modulo the corresponding subgroup. The FQ points of the space. So these are kind of classical objects, smooth representations of my group over a local field. It's kind of the classical object of like local elements. Now,
is this meant to be the value of the theory on the subject?
The value of the theory on this is an object of this two category, right? So the value of the theory on FQ bar on this circle is the collection of all of these ramification things. I was giving an example. This example actually you could draw by QFT pictures. If you take the circle, there's a natural thing to draw, which is a disk. Right? The disk is a manifold with boundary that circle in this formalism. That means an object of the thing attached to the boundary. That's what this guy is.
So it's the two category of GK categories.
It's a two category of GK categories, and there's a unit, a kind of a unit in there, which is the spherical module. That's the disk. Before, by the way, I put a double coset. I had basically, I guess my notations have shifted continuously, but again, this is the loop group and the positive loop group. Before I looked at the double coset, and I said, that's a sphere. So that was two disks glued together. That's the endomorphisms of this guy.
Can we do this? So this is like if you started with the local field of QT,
Yeah,
then you can kind of decrease the dimension by 1 by going FQ bar,
exactly.
right? But what happens if you start with like a mixed characteristic local field?
Well, I could still go to, I think the right thing to say is take the maximum ramified extension, right?
Okay.
And that's, I get rid of Frobenius. So I could still, in the legal picture, I still have this extra sum. So the Mignon, I think it's like, our two manifolds still look fibered over a circle. Our global three manifolds are not. The manifolds are. So, all right. So, Okay, but I'm not trying to get very categorical. I want to get back to more classical things. So the way, what did I do before? I said the line operators had to do with this categorical thing, but the loop operators, that was taking a trace. That was kind of decategorifying. The same way here, I don't really want to spend time on this level, this high categorical level. I'll take a trace of Frobenius. And that's where I'm going to get to local fields, right? So the point is that my picture of the local field, not my picture, Giesler's picture, the picture for a local field, right, is a two manifold. So here I think of my local field, for example, FQ Laurent series T, or maybe QT, or finite extensions thereof. The picture of those is something like it's a two manifold, but really it's a kind of a two manifold fibered over the circle. Only one I can draw is a torus. I should draw a chi model, but and the idea is that this topological field theory, once attached to this, so if you like, I like these SAT type analogies. This is to the representation range of the dual group as this two category as AG of the circle is to the representation category of the dual group. So that's what we did with line operators. We said there's a categorical version, or you could decategorify and get loop operators. So here, this is the surface version. These are surface operators, and then you can take their traces, and now the point is that this category is something we really care about. This is what the local Langlands story is about. I actually introduced this category last time. I said this category is something that contains the category of smooth representations of my p-adic group, my group G over my local field, which I guess I'm now calling K. But whatever. These categories.
FB is.
Yeah, this is my FB. FB is my field of.
And that you drew a torus.
Yeah, FB.
And that as the
Spec of FB.
spec of it.
Yeah, this torus is kind of a stand-in for spec of, it's some topological avatar of spec of it. And so, I claim that this, in the theory of automorphic forms, you care about this category of representations. And so that's true. In fact, but I also claim that this wasn't the full answer. And if you like the full answer, it's exactly what you would expect now. You can now go, and this is basically what Xinwen Zhu has explained. In the function field setting, the true full answer here, it's kind of forced on you, right? This is going to be what it really should, the whole thing should be the trace of Frobenius on whatever two category I had before, AG of the circle. I don't have a choice. And this is, I can write this concretely. It's like this, some local shtukas with singularities or whatever. There's a concrete space here. You can write down what this thing is. There's a concrete set. It's sort of take the group G over FQ Laurent series T and take some Frobenius twisted conjugate. Okay, let me not write it down. So there's a concrete category you can write down, and in fourth menu, another version of this is the Fark-Fontaine sheet on Bungie of the Fark-Fontaine curve. There's an answer from this in the number field setting. This is the answer that appears in Fark-Schulze, some version of this. But what I'm trying to say is that this local Langlands category that has this interpretation in terms of surface defects. Okay, and why do we, and why do we care? Why does local Langlands, or why do automorphic forms people need this local category? Well, because of ramification. Because what you are interested in is, as we've seen in Mignon's talk, it's essentially you essentially never want a compact three manifold. You're always dealing with compact three manifold with some singularities. So that in the theory of automorphic forms, what I really would like to do is I have my global field. This is playing the role of spec of the global field, but I have some ramification. I always have some primes where something interesting is going to happen. And I beg you to suspend disbelief before when I just wrote automorphic forms without talking about level structure. What you really care about is M with along you want the vector space associated to a 3-manifold with some decorations. And where do those decorations live? They live exactly, here's the boundary of the tubular neighborhood of these circles. That's the local category. So I pick at each prime, but at finally many primes, I pick some interesting local data. They're objects of my category, say representations of this group. Or concretely, you could just take level structures. I said that the representation I really care about are things like functions on G of my field mod some subgroup. These are the kind of representation I care about, and this would be if this is the Iwahori, this means it'd be a Iwahori level structure. This is the notion of the level structure. I look at this in automorphic forms with prescribed level structures at some prescribed primes. So this is the kind of thing where you look at you look at the upper half space mod things like gamma naught of n. Before I had a picture of SL2Z, upper half space mod SL2Z, really usually look at some interesting congruence subgroup. And that's what's prescribed by this. The n is the product of these primes. Naught maybe means the Iwahori. So that's the those labels are telling you which subgroups to take. Okay. So that's the role. So that's in the TQFT picture. You have a vector space where you attach these data. So it's a very natural setup for where ramification comes from.
Sometimes people use the word level. This has been confusing. Sometimes people use the word level in automorphic form.
Yeah.
Say it's not actually a function, but it's actually considered a line.
That's
a different kind of.
no, that's the weight.
Well, just for SL2Z, we talk about modular forms of level K. We say it transforms with the power of C tau plus
That's weight.
D.
That's weight.
Okay, that's weight.
Yeah. So weight will can appear also, but that has to do with what I put at the prime at infinity, which I'm ignoring. But
The weight is going to come.
But the level is saying what's congruent subgroup.
Is there any hint looking at congruent subgroups as beginner that would show some two-category structure?
Well, I'm saying that the congruent subgroup itself doesn't care what you put on it, right? It's not like it knows that there's a two-category, just like the global field doesn't know necessarily that you want the vector space of automorphic forms, right? You could do other things with global fields. The theory of automorphic forms knows if you want something well, you want a vector, you know that there's some category. So in the Langlands program, there's secretly always a category. People don't emphasize this very much in the classical theory. But when you're picking level structures, it's it has to do with usually people talk about irreducible representations of p-adic groups. These are the kind of data that specify levels. Well, those sit inside of some category. So that the category attached to this local field, that's where the local data sits in the theory of automorphic forms. So you don't know that it's a two category. The fact that it's a category is very natural. The two-ness comes from the fact that there's an extra circle here. And you could actually have gone and tried to get that category as a trace of Frobenius on something deeper.
Can you say what that is in the p-adic case?
What this category is?
The trace.
Yeah, so I don't know if that as a theorem. So I think that what this category if you want in the p-adic case, in the
But it's meant to be a refinement of smooth representation.
Yes. So this category, I tell you what this category is. P-adic case. You look at the fun G of the Fontaine curve associated to your local field, and you look at the category of sheaves on G of so that's the answer that Farg and Schultz tell us, and there's a very natural way in which the category representation, so Nick asked this question last time, there was a natural way in which you can see the category representation sitting inside of here. Xinwen's answer, let me just a second. Xinwen's answer in the function field getting, which is very close to Laforgue, Xinwen and Laforgue would say something which has essentially the same set of points in some sense, but there's a different model in the function field setting, which is you can look at G of, I'll mess this up, but I'll mess up for a second thing. So you can look at sheaves on, take this group, the loop group over FQ bar, and I want to look at F conjugation. It's almost like I'm doing class functions or class sheaves. I look at conjugation, except I do Frobenius twisted equivariant. look, Frobenius twisted equivariant sheaves on this.
Hmm.
Both of these sets have a set of points as these Kollwitz G isocrystals, isomorphism classes. Both of these are labeled by these. But so this is literally what you would get by taking trace of Frobenius on the loop group categories. So so in the, and Schumann has all kinds of theorems of that nature. And he doesn't say it literally in the two categorical language, but kind of that's basically what he's doing. But maybe he does say it in two categorical. Anyway, that's certainly what he's doing. Okay. So anyway, but again, this is just what you get by taking so here you have this twisted circle. This almost looks like a circle, but twisted by Frobenius. Okay. Yeah.
With automorphic forms, there's normally a growth condition, a moderate growth condition. So is that captured?
That's much beyond my pay grade. I mean, I think again, the basic thing that I'm completely ignoring is anything that has to do with with Archimedean things. And there's some, but I mean, yeah, let me not answer that since I don't have this.
And what is the relationship between this and the smooth representations? Is there like a functor?
Yeah, the category of smooth representation, the full subcategory here, it's basically the category of things that are supported on that. There's a stratum inside of here which looks like point mod G of FP. That's not quite right. There's this J groups, some diamondy crazy thing, but basically G point mod this group lives inside of here, and so sheaves on that are representations. Again, in assumable condensed, blah blah blah, whatever. You have to say.
They're smooth representations, so there shouldn't be any condensing.
Well, the full category, the full derived category, you have to say what it means. So solid sheaves. But anyway, it's not before I dig my.
Yeah. Okay.
But anyway, this is but these are so the category of smooth representations appears in here in terms of sheets basically supported on this point. There's an open point labeled by a group. There's actually other points labeled by pure inner forms of it.
So when they consider sheets, there's no like finiteness condition. Because
No.
these smooth representations.
No, there's no finite. Yeah. Okay. All right. So that's surface defect. So the point is that in the Langlands program, we have this notion of ramification. In geometric Langlands, this notion of ramification. So there's a paper of Gukov and Witten about ramification in geometric Langlands in terms of surface operators. So this is some descendant of that. Okay. And by the way, if you have primes that are not ramified, at all other primes, you can write down, where nothing interesting is happening, you still can write down the same Hecke algebra. You can still write down the same line operators. So at all unramified primes, you have the same unramified Hecke algebra acting, but then the ramified primes, crossing with time, I have to draw these surfaces. So there's places where I have to avoid, but around them, you still have the unramified Hecke algebra. So away from the surface defect, you have the usual line operators. Okay, so that's the story so far. So now, I think so far the TQFT. What has the TQFT done for us so far? It's an organizing tool. It's a way of saying all of these structures at once. It helps predict some things. For example, these kind of the relations with these these Frobenius traces are interesting statements, but it hasn't. So far, it hasn't given us. It's just sort of a convenient way of organizing things. I think once you get to here, maybe let me draw one more picture that I said last time, which was this space of shtukas. I could take as a curve over algebraically closed field, and I can imagine acting by some line operators. So I have so I can take a picture where I can take this. Okay, maybe actually, never mind. Let's move on. So they can explain this space of shtukas as a trace, and that's a deep theorem of AGKRRV, that these cohomology space of shtukas really appear this way, from as kind of a trace. If you take the trace of Frobenius composed with various Hecke operators on the category assigned to a surface. So not just Frobenius, but Frobenius with a bunch of line operators. So these are my line operators. But now, so now this is a picture where I cross this with a circle. It's like not quite crossing with a circle, it's Frobenius circle. And then I have some places where I put in these loop operators. Then that's a picture we had last time. And there it's a deep theorem of a PKRV that this is the cohomology of the space of shtukas with suitable lengths. So anyway, that's a kind of a theorem that, you know, I don't know if they were thinking, they weren't necessarily in QFT language, but this is something that's very natural for them.
I'm very confused. The shtukas with legs, I understand,
Yes,
but what is, when you say a
Yeah.
surface?
Yeah.
What do you, what,
So I
do you
mean-
literally mean what you wrote?
yes, I have a curve, I take a curve over a finite field.
Ah, okay,
I have
so
a
it's not
cat-
literally a surface, okay. No, I'm
Yeah,
just,
yeah, yeah.
okay.
I have to have a curve over a finite field. Sigma bar is its over algebraic closure. So I have a category attached to the curve over the algebraic closure.
Okay.
This category has some functors. It's Hecke functor. These are these line operators. And I can take the trace, before I was just taking a trace of Frobenius, take a trace of Frobenius composed with these operators. That's a new interesting functor. And that's this thing I claim is drawn in the TQFT given by this kind of picture. Instead of just taking this mapping cylinder of Frobenius, I put some lines here, these which are decorated by these line operators. And the claim is that the trace of Frobenius composed with these Hecke operators on this category is the cohomology of the space of shtukas, which is, this is a theorem that justifies the picture I drew last time. I drew a picture, I claimed, oh, this picture corresponds to the space of shtukas, and you'd be like, great, you can call it whatever I want. But this is a theorem that makes sense of that. That's a deep theorem that makes sense of that picture.
But usually when you have like the cohomology or something like the space of shtukas.
Yeah.
And you have your group G, I mean, this is true even in like the Schmor varieties.
Yeah.
There's usually some representation of G.
Well, there's a label that's purple. My representation is purple. The Hecke functors are labeled by representations of the dual group, right? I need to tell you which Hecke functors I do and at what points. That's the data that gives me the legs. There's representations of the dual groups. There'd be a minuscule
So
representation.
there's a representation of G, which is showing.
G check, that's a representation.
That's fine, yeah.
Hecke functors correspond to representations of the dual group. So each of these guys has a label which is representation of the dual group.
I'm just saying on the right, usually there's a representation of the group which is built in. On the, if you really mean like cohomology space of shtukas.
I do, but I don't, there's a representation of the dual group. Right? There's
That's fine, I'm not gonna like quibble about G versus.
No, but here it's important, right?
Okay,
You know, it's Shimura variety, you pick a minuscule character of, you know, weight of the dual group. That's your Shimura data, and that's what this is, this way. Okay. All right, so now. Okay, so now let me pause. Now I want to transition to something. So if you got lost here, let's regroup. And what I'd like to talk about now is what I think the kind of the richest part of the story, both physically and well, I don't know. Let's just say physically. So the richest part of the story is a theory of boundary conditions or codimension 1 defects. So I've been doing defects that are bigger and bigger dimension. I had 0-dimensional defects, 1-dimensional defects, 2-dimensional defects. Now I want to talk about 3-dimensional defects. And they're the richest because, you know, they're the biggest, well, they're the biggest. So now now when you talk about these, let me start with something. So what kind of things can you imagine doing? And I'll admit straight off the bat that the only pictures I'm going to draw with these are going to be very boring. I'm not going to do interesting boundaries, but the only pictures I'm going to draw is like draw a manifold cross an interval and write in one end of that interval. That's basically the only kind of boundaries I'm going to talk about. But okay, one more thing you could do is, I guess you could do something like this. I can take a manifold cross an interval, and I can imagine having take the manifold cross time 1/2. That's a picture that's analogous to the pictures I drew before, right? This is just a 3-dimensional version. Here I have, and the cool thing in physics is that, you know, since you've separated this into 2 different halves, you can allow yourself to do two different theories of the two parts. There's nothing for they're not connected anymore. So you can imagine doing two different theories of the two parts. This is what physicists would call a domain wall between two different. So kind of the morphisms between TQFTs are these domain walls. There's these co-dimension one defects. They're the natural category structure of TQFTs. So for example, I could put my favorite group G here. And here I'm studying the theory of automorphic forms for my group G. But on the other side, I can pick some other group H and studying the theory of automorphic forms for this other group on the same manifold. And if I have such a defect that has one side has G and the other side has H, I get maps between space of automorphic forms. So this is where Langlands functoriality comes in. So in the theory of Langlands corresponds, one of the deepest things is Langlands functoriality is how do you relate what are maps between spaces of automorphic forms for different groups. And that's captured physically by this theory of domain walls between these two different theories. It's easier though not to think about this way. If you'd like, you could fold the picture, just like you would think of, well, I can fold this picture around and reduce this, in some sense, you can reduce this to just studying the picture of just having a single group and having a boundary. So I'm really only going to look at this kind of picture. In other words, on the other side, I'll have a kind of a trivial theory. I'll have, so a boundary is a special case, where on the other side, I have something trivial. But of course, if I put my group to be G times H, the theory of kind of boundaries for G times H includes that theory. So that's just a comment that what I'm going to talk about includes this sort of, but in a kind of hidden way. So I'm going to talk about the theory of boundary conditions. Boundary theory. So these are co-dimension one defects that live on the boundary. So I'm not putting anything on the other side. Okay. Now this, so this in the theory of automorphic forms, this corresponds to something very central, which is the theory. This is given by the theory of periods of automorphic forms. So this is what I want to talk about next. What are periods of automorphic forms? And what does this picture suggest to me? Well, on the other side, I put nothing, right? So that means here I have the space of automorphic forms associated to my three manifold, and on the other side, I have nothing. Nothing means I just put the ground field, whatever my coefficient is. Okay, I've been very sloppy, but where my coefficient is. But so it's just a functional, it's just a measurement. So a period is going to be a functional on my space of automorphic forms. Now, if you're very sloppy like me and you don't care about duality, you can imagine dualizing this picture and just think of it as an element of the space of automorphic. Except that these won't be elements that have the kind of growth conditions that we would like. So we can think about functionals on automorphic forms. We can try to represent
Identifying the dual space. With the
I can imagine identifying the dual space, except that my automorphic forms tend to have strong growth conditions in the function field setting. Maybe I want compactly supported functions or something like that. And these functionals will be representable by things that are not compactly supported. So loosely speaking, I can think of them as elements of the same space, but really it's elements of the dual. But I'll be very sloppy about that duality. Okay, so yeah.
So this is the four-dimensional theory that you run over.
Yeah.
So the two theories on the two sides of the attached from vector spaces to that domain wall, I guess.
So I have a theory attached. So I have a three manifold here. I have my theory. One theory attaches a vector space here. Here I put another theory that attaches a vector space here. The domain wall, the way it's realized in this QFT picture, the domain wall gives a morphism. So this picture gives a morphism between the vector space attached to one end and the vector space attached. I mean, that's basically what you were saying with that. I think of morphisms as maps.
So I shouldn't think of that as being boundaries of the two domains.
No, it's just something that lives in the middle. It's an interface, just like before I drew this picture. Okay, and now I'm saying this is an interface. There's something here, and there's a map.
Okay, but since we move back to this picture, I mean, I don't know what the screen stuff in the middle means.
Yeah.
But to get like this functoriality map, you need some relationship between H and G usually, right?
Well, you can.
How is this reflected in this?
Well, I'm just saying I'm just saying by definition, such a domain wall, an interface between theories, will be a consistent way of mapping automorphic forms, G to automorphic forms for H for every input here.
Oh,
not just for three manifold, for two manifold. It'll be a way of taking the
Right.
entire theory of automorphic forms for G, entire theory of automorphic forms for H. These are really hard to come by. I'm not saying.
yes, but usually that's predicted because in terms of something simpler between the dual groups.
That's right. Well,
So I thought that's what you were going.
no, I'm talking about, right now I'm just saying, we can talk about arbitrary ones.
Okay,
The ones that usually do get called by Langlands, I'm expanding what I'm calling Langlands factoriality. There's going to be many such things, and they don't all come from maps of dual groups. Some of these will come from actual maps of dual groups, there are more. So we're trying to understand what is the structure of these collections, and and you know, as Mark is saying, these are hard to come by, right? Just and like domain walls in physics also are very rich things. There's some ones you know, but there's lots.
so it's just like, really is just a picture.
Regarding the
Oh, no, well, no, it's just like everything before, right? I mean, I can make a definition of what this is. It's not just a picture. The question is, can I construct one, right? You're saying Langlands functionality is hard. I'm saying it's hard to construct these. There's ones we know, you know, like Eisenstein series will be an example of this.
But it's not that this is predicted by some other structure. It's just that you're looking for the structure.
That's right. I'm just saying that in a four-dimensional TQFT, you have all these different things. And I've been saying, oh, you should have operators of everything. And in the theory of automorphic forms, they each have a meaning. These are Langlands functionalities. Now we have to calculate what all of them are. That's you know, try to describe what are all the different possible Langlands functionalities.
If we take a much simpler case, supposing we do G and H are finite groups.
Yeah. Yeah.
So then I think your interface would be something like would involve something like a reduction of structure group.
It could,
Or
but there
some
be many.
other group L with a homomorphism of G to G of L to G and L to H, and that's the way you would be
That's an
relating
example.
G and H.
But there are many other examples, right? I could take any space Z on which T and H both act, and that gives me an interface.
Does that give you H and H are finite instead of all of the
Yeah.
interfaces?
Yeah, so I mean, it's like some kind of bimodule for the, you know, group algorithm G and group algorithm H. And those don't need, you know, there are many, but yeah, so in the case of finite groups, we can describe all of these completely. Right now I'm being agnostic, as Mark, you know, I'm just saying, what is the structure? And now I want to say, what are some examples? We're going to talk about examples. I'm going to focus on periods. And then we'll see what is the structure and what does physics predict about the structure of them. The point is that you get interesting predictions. I mean, that's going to be the punchline, right? By Friday, or tomorrow, we try to explain that you can make interesting predictions about the theory of periods by thinking about them this way. Or Langlands functionality. Good focus on periods. Okay. All right. So now let me tell you a little bit about periods. So these periods are going to be linear functionals on automorphic form. Let me give you some classical examples of periods, and we could, you know, so where do these, what are typical examples of periods? So the way these usually arise is something like this. I'm going to take my group G, the easiest ones arise by taking my group G, and I'm thinking about, I've taken a space X, maybe X will be just a homogeneous space for some subgroup of G. And so if I give you so what's given us, so if you like, right now, really, I'm using the letter X because I prefer it, but right now I'm just giving the data of a subgroup of G. So given what's a notion of an H period, if I'm in the geometric setting, I could look at the moduli space of H bundles on wherever I'm living. There's a map from the moduli space of H bundles to the moduli space of G bundles. So I could take an object here, my automorphic forms of maybe where objects would live here, I can pull them back to here and integrate, push it forward to a point. In the theory of classical automorphic forms, you might write a locally symmetric space associated to a subgroup, and that maps to the locally symmetric space associated to your group. You could take your automorphic form here on this locally symmetric space and restrict it and integrate. And just to draw a picture, right? So the classical periods, if I take a modular form on the upper half space, this is my shorthand for modular form. If I give you a modular form, there's a couple of interesting periods you can look for. What are my group here is say, let me drop that. That's PSO2 is my group. So there are a couple of interesting subgroups you can look at. So for example, you could take the subgroup of upper triangular matrices. in PSL2. And that course, this construction corresponds to looking at a horizontal line. That's this inclusion. And so you can take a modular form and integrate it along a horizontal line. That's called the constant term. They call this the Eisenstein period. So the Eisenstein period takes a modular form and integrates on this line. This gives the constant term of the Q expansion. So that's an interesting measurement.
Where H is V.
So here H is U. The example here is my subgroup, I pick U. You might be a little more, you might say, maybe I want to take the group U with a character. Maybe I don't want to just integrate it along this line. I can integrate this line against the character. So maybe it's the data is not just a subgroup, but maybe like I also take some kind of affine bundle. I also take some twisted version of this. And so instead of just integrating on this line, you might integrate against a character. And that's called the Whittaker period. So it fits in the same kind of way, except it's a twisted version of integrating here. That gives the linear term, leading to the Q, what's it called? Yeah, Q, the term of Q, the coefficient of Q, the Q expansion. So that's example periods. Another example of a period is I could take for my subgroup something very different. I could take the diagonal matrices. And if I take for diagonal matrices, I end up getting this guy. And I think so I can take a modular form and integrate it against, maybe I want it to already be a cluster form for this integral to be reasonable. And this guy is, this is what it's called the Hecke period. And what Hecke calculated that this period gives the L function of the modular. So you can describe the L function of modular form as this measurement. Maybe I'm thinking the value of this L function, or I don't put something to integrate against. So these are natural measurements of modular forms, and they come in this way from a G space. I feel like maybe I only needed that subgroup, but I really want to think about it as not being about the subgroup, but it's the G space.
How would you describe modular symbols?
I would. I don't know much about modular symbols. But probably there's a good answer, but let me not. Okay. And so yeah, so you can do versions again twisted by an additive character. You can incorporate that and let me not worry about that so much. So these are interesting measurements. They're interesting measurements of modular form that tell you, for example, the L function of the modular form, its constant term, its Fourier expansion. So the idea is I find my space of automorphic forms. You ask, what are good measurements? What are interesting measurements of them? And the claim is that these measurements are not just measurements that make sense for a fixed three manifold. They make sense in the entire theory of automorphic forms. They make sense over any place where I can do the theory of automorphic forms. So this is what makes this an interesting, like a boundary condition. It's not just a measurement for one particular space. It's kind of a coherent way of measuring automorphic forms for any input here. So that's now they what it turns out is you need something strong. So you actually don't
Wait a
need.
second, suppose you have a congruent subgroup, so then you could have the constant term associated with the Q expansion at different cusps. So
Yeah,
I'm trying to understand what you're saying. So then, there were many Eisenstein periods. Right? If I didn't take TPSL2Z, but a fundamental domain for some congruent subgroup, have a bunch of inequivalent cusps.
yeah.
And if I have an automorphic form for that, I could talk about the constant term. So
Yeah, I mean,
the different.
But there are many subgroups I could take associated with these different subgroups.
Well, that's right. There's a different
So
parabolic subgroup for each of those.
Yeah, so for each parabolic, I mean, so here I was giving an example, you didn't have to talk, but I can give you, I'm not, so there are more examples, but let.
I'm just trying to understand your statement that it should make sense for the entire theory of what.
I'm just saying that I'm not trying to, right now, I'm not trying to tell you yet what all the periods are. I'm just trying to say that this choice, look at the subgroup U of PSL2, or this space G mod U, which is A2 minus the origin. That data, I can use it to do a period on for any number field. This gives a consistent way of making measurements of automorphic forms in any setting, in all of the settings we've looked about. So.
Oh, I thought you were varying the group when you said.
No, I'm fixing group. Yeah,
Okay.
my fixed TFT, right, I'm saying I'm evaluating this TQFT on arbitrary three manifolds. This measurement, this is a local boundary condition. I can put it on any geometry I want. Yeah, now it turns out you don't need this group, you don't need this to be a coset space. I mean, you don't need this actually to be transitive. To define it, in fact, the most important, well, I don't, the earliest period is just take the group to be the multiplicative group acting on X to be the affine line. So this is the Tate period. Yeah,
You say you're fixing a group, what's that? Your group is split or what?
my group G, I took the last time to be a split group over the integer, so I don't need to think about that. Because I want the theory to make sense everywhere.
And then do these subgroups also have to be split?
Yeah. I mean, you could do more, you know, there's more elaborate measurements that will make sense only in certain, I mean, yeah, right now, let me just for now, just.
Is it you're saying you can evaluate this field theory on any,
Yeah, if I want to evaluate on
is
anything.
that related to the splitness of
Yeah.
the group or?
Yeah, but I mean, again, if you don't want to be defined on anything, you can define, you can take a group defined over some other number field and you'll be able to evaluate them. That's. Yeah. Okay, so there, I don't know, you don't actually need the group to be transitive, the action to be transitive, you could write down this version here. What you do need is you need some strong finiteness conditions. So this space, so I could write, maybe I'll write next time what the period is associated to a non-homogeneous space. But there's a key thing is that the G action on X needs to satisfy some very strong finiteness, conditions. And this is not quite equivalent to, I think, but it's roughly equivalent to, it needs to be a spherical variety. So this is where the theory of spherical varieties, I think this is an observation, among other people, Yanis Sikourides, so the role of spherical varieties here is that as kind of a way of, so a spherical variety is a non-abelian version of a toric variety. If G is a torus, this means a toric variety, like that fine line. But this strong finiteness condition is needed for all kinds of things. They give you a kind of strong version of the locality that I want of this. I haven't formulated what I want of this, but you can write down these intervals. I didn't need at this point this to be spherical. The kind of locality I want, the kind of TQFT properties I want, seem to be very close to this finiteness conditions. And okay, I think I'm over time. So maybe so what I'll do next time is I'll tell you, try to fill out this theory of periods to look like the kind of pictures you could do from a TQFT. So what happens for a two manifold and a three manifold, you know, just how all these things fit together. There's a lot of structure that you get, and that structure is seen in the theory of periods. And then I guess in the remaining time, I'll do the length. I'll do the other side of the length. Okay.
Any more questions?
I did have one question. So we went down, I think, to the case where the manifold was one-dimensional,
Yes.
we had a two category.
Yeah.
So there's just one more step to go.
Yes,
Can we go like the one remaining step?
we did. You might not have noticed it, but so the point is that in this TQFT, if you believe this TQFT language, if you want to think there should be a three category attached to a point, and that three category is the three category of boundary conditions. Up to some quibbles we can discuss, but
Well, my first question is,
Yeah.
what was the point?
what was the point? That's unclear.
Just like,
Yeah, I mean, like, you know, I think a point is something like, well, there are several points, but in a TQFT setting, in the world of
Yes.
honest manifolds.
no, that wasn't my question.
Yeah. Well, that's a really hard question too, that we don't really know the answer to. That if you're just doing honest TQFT,
Yes,
there's a really interesting question is what is the three category attached to a point? And that name is just a name for the three category of all of these boundary theories. So these boundary theories form a three category for the same, well, yeah, so they form a three category for the same kind of picture of interfaces. And we, on the Langlands dual side, on the Galois side, we know pretty much what it is. On the automorphic side, we don't really have we don't really understand what it is. So even in the real world.
I just mean even in the local, you had a local setup, right?
Yeah, I mean, you can imagine a good point is spec FQ bar. And on the Galois side, I would know what to attach to that, but automorphically, I don't know what kind of objects. Basically, because in algebraic geometry, you don't really know what pictures like this mean. I don't know. Like this manifold a half plane is not a very complex algebraic. I know it's not a very algebraic geometric object. So this is where a boundary lives, and we need to be able to make sense of this picture to make sense of what. So I think no one has. As far as I know, no one has a really good understanding of.
I mean, the funny thing about this is that as the objects get simpler, like the categorical.
Yeah.
Things get more complicated.
Exactly.
And here, like, you just have FP bar, so there's like basically no interesting.
That's right.
information.
I
But
mean,
it has to be some very canonical thing.
you would naive guess would have been it would be some 3 category of 2 categorical representations of G over FQ bar. That's the kind of thing you'd like to say. I mean, that was kind of a little too naive in the circle case anyway. On the B side, that is correct. You can make sense of that. There's some sheaves of 2 categories, incoherent sheaves of 2 categories over a point on the group. Anyway, there's a 3 category you can write down. But or Hermann Stefan. But so we have some idea on the Galois side what to do, but on the automorphic side we really don't. So I'm going to give you examples of periods, but I don't know what the collection of all possible periods. Like before, I gave their result. I claim all line operators are given by representation of dual group. All surface operators, like some categorical representation. I don't know what all periods are. We have a lot of examples. And you learn a lot about those examples by thinking about them this way. And they're more than you realize they're more than what you might first think about, but we don't really have a sense of what they all are.
David, something's bothering me from the physical point of view. I mean, we look at boundary theories.
Yeah.
We should be able to modify it. First of all, boundary theory is not the same as a standalone theory, but we should be able to take any 3-dimensional theory with 8 supersymmetries,
Yep.
G symmetry, and couple it.
That's what we're
So
going
are
to do.
you claiming implicitly to have a classification of?
Oh, I never claimed a classification of anything. No. But in fact, most of what most of what we I should give there's most of what I'm talking about is described. It's very schematically. There's a long manuscript that I wrote with Yanis Sakelaridis, Akshay Venkatesh, and the nonsense that I'm talking about TQFTs, arithmetic TQFTs, is all in Appendix B. So the last 2 talks, this is a place where some of these words are said. But that manuscript is very much based on what you just said. So the idea of the boundary theories is going to be take a symplectic variety. We don't need hyperkähler geometry, but you take a holomorphic symplectic or algebraic symplectic variety with a Hamiltonian action of a group. Those give boundary theories, and those are the ones we study, not for arbitrary ones, but things like cotangent bundles of certain.
So they're examples of boundary theories.
Yeah. So we'll talk about next time. The examples of boundary theories we study are things like T star of X, where X is a spherical variety for G, and that's a Hamiltonian action of this group. And so that's the kind of data that defines, if you decouple from G, would define a 3D, 3D n equals 4 theory, which is the kind of thing you want to define as a boundary condition. Yeah, so secretly, that's why I started here. There was a subgroup H. I said, don't fixate on H, look at the coset space G mod H. And then we really are going to say, don't fixate on that space either, fixate on its cotangent bundle. And that's kind of the more fundamental object. So really, it's not about, so it's something like T star of G mod H is somehow a better thing to think about it than just H.
Right, thank you.
Yeah.
So I think it's going to be a boundary theory by looking at the.
Yeah.
So when you said earlier about the 3 category of boundary, so then you're referring to just the category of functors from trivial theory to the restriction theory or something like that.
Yeah. Exactly.